Hello everyone and welcome to Webcam tutorials. Here in this video we are going to perform simulation of 1D steady state heat conduction inside a rectangular bar. Two ends of the bar are subjected to constant temperatures. After performing the simulation, we'll validate the results with the analytical results. At each step, I will try to give you a bit of information. I will also try to explain what is going inside the software while performing each step. So let's begin it. Before starting the simulation, let us first go through the problem statement. So here is the problem statement. We have to first create a bar that is having a rectangular cross section. The length of the cross section is of 100 mm and the height is of 40 mm. The length of the bar is of 800 mm. After creating the domain, that is the bar, we have to assign material, that is aluminum alloy AISI 1060. One end of the bar is at a higher temperature of 100 degrees centigrade, while the another end is at a temperature of 20 degrees centigrade. All the remaining four faces are insulated, that is, there is no heat transfer from these faces. It can also be called as these faces are insulated. So let's go to the Solidworks. The first step in any simulation process is to create the domain or the geometry. So in our case, it is a rectangular bar. To create that bar, first we'll go for the sketch and we'll select here right plane as a sketching plane. Now here we'll draw the cross section. So we'll go for the center rectangle and we'll create one rectangle like this. Now we'll go for the smart dimension. Now this one is of 100 mm and the height is of 40 mm. Now after creating the cross section, we'll exit the smart dimension and we'll exit the sketch. Now we'll go for the features and select here extrude boss feature. Now from here we can see that we have to extrude it for 800 mm. So in the depth we'll enter here 800 and OK. So here in the first step we have created the domain or the geometry for the simulation. After creating the domain, we have to go for the Solidworks simulation. So first we have to activate the Solidworks simulation tab. For that you can go for the Solidworks add-ins and you can select here Solidworks simulation. If you cannot find here, then you can go for the settings, add-ins, and here you can check Solidworks simulation on both the sides and just click on OK. Once you click on OK, here you can find the Solidworks simulation tab is added over here. So you can just click on the simulation. Now here we are going to start a new study. So we'll just click on this new study. Now here there are different kind of studies are available. For our case, we are going to perform this thermal simulation. So we'll select here thermal simulation. Here you can give it any name. So here in our case, we'll give it name as a 1D steady state conduction. And after giving the name, you can just click on this OK button. So once you click on this OK button, you can find here that another tree is available, that is the simulation tree. So let us understand each and every step of this simulation process. After creating the geometry and activating the Solidworks simulation tab, the next step is to apply material to the component. So to apply the material to the component, just right click on the part and select here apply or edit material. Now here in our case, we have to apply the aluminum alloy AISI 1060. So from here we'll select aluminum alloys, select here 1060 alloy and just click on the apply button. Once you apply the material, you can see that the appearance of part gets changed according to the material applied. So this is the third step in any simulation process, that is to assign material. After applying the material, the next step is to apply the boundary condition in the form of thermal loads. So from this tree you can see that as we have assigned the material, you can check here the check mark is available on the part. Now here as we are having a single component, so there is no need to give the connections. The third part is the thermal load, that is the boundary condition in our case. So as we know that one end of the rod is at a higher temperature and second one is at a lower temperature. So just right click on the thermal loads, that is the boundary condition, and we can select here temperature as a boundary condition. Once you select the temperature, we know that we have to give the temperature in the form of degree centigrade. So from this drop down we'll select here the Celsius, and one end is at 100 degrees centigrade, so we'll specify here 100 degrees centigrade. After giving 100 degrees centigrade, we have to just select the face that is at 100 degrees centigrade and click on OK. So you can note that this face is given a boundary condition. Now similarly we can give another boundary condition at over here, that is 20 degrees centigrade. And for this also we'll just right click on the thermal loads, select here temperature. From this drop down we'll select here Celsius, and this end is at 20 degrees centigrade, so we'll specify here 20. After specifying 20 degrees centigrade, we'll just click on this face and click on OK. Now here we have applied the boundary condition to the two faces. Now we are having 4 faces left, and we know that the lateral faces are having no heat flux. So to apply the boundary condition of insulated, we'll just right click on the thermal loads, and here in this case we'll select here heat flux, as we are having 0 heat flux. So we'll select here heat flux. By default it is given 0 heat flux, and we also want to give it 0 heat flux. So we have to just click on the surfaces that we want to give 0 heat flux. So we have to select all the 4 lateral surfaces one by one. After selecting all the 4 surfaces, you can find here all the faces over here, and you have to just click on OK. So this is the step in which we have applied the boundary conditions to the domain. After applying the boundary conditions, the next step is to generate the mesh. As we know that this bar is made up of number of infinite small elements, and it is not feasible to solve the governing equation at each and every point. So in order to make this problem feasible, what we are doing is we are dividing the entire domain into the subdomain, and we are dividing into the subdomain such that the numbers are feasible to solve. So to generate the mesh, we just right click on this mesh and we'll select here create mesh. Now here you can control quality of the mesh, so we'll go for the fine. Fine mesh gives the better result, but it will take more computational time. For this instant we'll select here fine meshes. From here you can control the parameters of the mesh, that is the standard mesh, curvature base, blended curvature base, etc. Here in our domain there is no curvature, so we are just selecting the standard mesh. You can also control the size of the element that is going to be created. Now for this case we are keeping it as it is, and we'll just click on this OK button. Once you click on this OK button, you can see that the mesh is generated in the domain, and the entire domain is divided into the subdomains. Once the entire domain is divided into subdomain, the governing equation is solved at each and every element. So here it is possible to solve the governing equations at each and every subdomain. If we want to find out some details of the mesh, we can just right click on the mesh and we'll select here the details. Now while performing any simulation, it is useful to notice that the number of elements that are generated. So from here you can find the total number of elements that are generated, that is in our case it is around 51,000. So it is a good practice to note number of elements that are generated, because it largely affects the computational time. So we'll just close it. So after generating the mesh, the last step is to run this study. So once we click on run this study, the governing differential equation of heat conduction is solved at each and every element that we have created during the mesh. So here you can find run this study. So we'll just click on run this study, and you can find here status of the simulation. Once the calculation is completed, you can find here that the color of domain has changed, and here also you can find the legend that shows the temperature, and the color shows a particular value of temperature. You can also notice that here the output temperature is in Kelvin, though the input was in degree centigrade. So let us first convert this legend into the degree centigrade, and for that we'll just right click on the results and we'll select here results equation, and for here we'll just click on OK. Now here we can give title to the legend that we are going to create. So we'll name it as temp, and into the bracket we'll just enter capital C, that is 4 degrees centigrade, and from here we'll select the metric system in which the temperature is in Celsius and just click on OK. So here you can notice that the legend has changed from Kelvin to the degree centigrade. So from this legend you can see that here the red color shows the maximum temperature, that is of 100 degrees centigrade, and this blue color shows the minimum temperature of 20 degrees centigrade. So as the boundary condition was such that this end was at 100 degrees centigrade, so here it shows the color of red color, that is of maximum temperature. The other end is at a lower temperature, that is of 20 degrees centigrade, and that shows the color code for the lowest temperature. Inside the domain you can see that as we move from the hot side to the cold side, the temperature inside the domain reduces gradually, and it reduces from 100 degrees centigrade to the 20 degrees centigrade. So after analyzing the result, we'll just right click on this boundary conditions and we'll make it here hide. So after hiding the boundary conditions, now it is time to validate the results with the analytical results. And for that we must know temperature at any point on the domain. So to know the temperature of any point on the domain, we'll just go to the plot tools and we'll select here the probe. Now we have to select any point on the surface over here. So once we'll select any point on the surface, here you can find the location of that point in the coordinates, that is x, y and z coordinates. You can also find the temperature at that point in the matrix, that is in degrees centigrade. So it shows that here as we have kept all these four lateral surfaces insulated, so there was no heat transfer from this surface, and the heat transfer was from this face to this face. Hence the heat transfer was 1D heat transfer. So the heat transfer is 1D and the temperature distribution inside the domain is a function of only this direction. From the Cartesian system we know that this direction is of x direction. So the temperature varies in x direction from the hot phase to the cold phase. So in order to validate the results, we must know the x coordinate, and from here we must know that the x coordinate is 327 millimeter. So now let's jump to the calculations for this temperature distribution. So here on the screen you can find the analytical formula that is used to find out the temperature distribution of 1D steady state conduction. Now here T of x denotes the temperature at any location x from the hot phase. T of h denotes the hot temperature. T of c denotes the cold temperature. Capital L denotes the entire length of the domain. Now once you input all the data, here in our case T of h is of 100 degrees centigrade, T of c is of 20 degrees centigrade, x is the location, that is 327 mm, capital L is the length of the domain, that is 800 mm, and T of h is 100 degrees centigrade. So after inserting all this data into the equation, you can find that the temperature that comes is 67.3 degrees centigrade, and from the numerical value it is 67.34 degrees centigrade. So here in this video we have set up a simulation for 1D steady state conduction inside the rod. We have found out the result at any point x inside the domain, and we have validated results with the analytical results. I hope you enjoyed this video. If you like this video, then please hit on the like button, share it and subscribe to this channel, CAD-CAM tutorials. Thanks.